So, if you have any questions, you can ask me right now. But first, let's start with an overview of the previous lectures. So, welcome in today's advanced array signal processing. Before we finish standard Aasp algorithm with two pre-processing steps, and then we went to subsection called as real value signal subspace estimation. This transformation from complex values to real valued cases, they are used in 1D unitary Aasp, and let's go inside of this 1D algorithm, 1D case algorithm. So we first transform our X using transformation. So first, let me show you one more time what we have for this transformation scheme. So you can see we have original X. If the number of rows is even, we'll have only X1 and X2. If the number of rows is odd, we'll have this X1. Then between X1 and X2, we need to divide these two things with one row of X transposed. And here you can see how we construct transformed matrix X. And if we have, one more time, the number of rows even, we'll have only real part minus imaginary part, imaginary part, and real part. So this will be equal to nothing in this case. So then we say that we have these eigenvectors E sub s, and this thing can be calculated using EVD or SVD. And the main thing here for 1D unitary Aasp, instead of array steering vectors and array steering matrices, we use transformed vectors and matrices. Here you can see how we do these things. So we use sparse left by real unitary matrix Q of size M, where M is the number of overall number of elements in our array. And here we introduce transform selection matrix, which is K. And for this one, we only need selection matrix 2. So for selection matrix 1, we use the real part of this multiplication. And for selection matrix 2, we use the imaginary part. And we end with this equation here. So, for example, we can compare it with our standard Aasp algorithm. So for standard Aasp, we have selection matrix times A times matrix phi equal to the selection matrix 2 times matrix of, let's say, array steering matrix. And here, the same things, but this one is transformed selection matrix, this one is transformed array steering matrix, and instead of matrix phi, we have matrix capital omega, where the diagonal elements of this matrix equal to the tangent of mu sub I over 2, where I goes from 1 up to the number of wavefronts or number of sources, small d. Then let's continue our lectures. And first, let's show what we have for this transformed array steering matrix and for signal subspace. So let me check what we have for online thing. Yes, everything is all right. So lecture number 23. Lecture 23. Today is 2022, November 22nd. And now let's write down transformed array steering matrix D. This one is equal. So one more time. The sparse left parallel unitary matrix of size M Hermitian times original array steering matrix. And for signal subspace, so E sub S, so we need to multiply, let's say, original signal subspace with the same sparse unitary matrix. Q of size M Hermitian times U sub S. Let's put this into the box, these three equations. And today also I will introduce you structured least squares algorithm. So the last one, before we have least squares, then total least squares. And for today, we need to go through the structured least squares solution. Then we can write down that, as before, signal subspace of array steering matrix is equal to the signal subspace for our, let's say, sources. In the same way, we can show, so this one and this one, they have the same number or the same connection as the signal subspace of the transformed array steering matrix with, let's say, transformed signal subspace. Or from this thing, we can say, from this thing, we can show that we have some connection between matrix D and matrix sub S with some transform matrix T, where T is non-singular. Matrix T is non-singular. And of course, we do not know this matrix T. It is some connection between matrix D and matrix E sub S. So I put this equation into, let's say, green box, filled with green color. Also, I will put all these, let's say, 3 lines into a box. And then we can show what we have for this multiplication inside of the green box. So let's start with E sub s. So the number of rows for me is equal to 2 centimeters here, and the number of columns, let's say, 1 centimeter. Or 1.5. 1.5. So this one is our E sub s. Here we have number of rows is equal to m, number of sources, number of columns is equal to the number of sources. Then we need to multiply this matrix with transform matrix of size 1.5 centimeter. Let's see this one, 1.5 and 1.5. So this matrix T is square matrix in this case. This one is matrix T of size D, D times D. And as a result, we have transformed array steering matrix D. Of size M times D. Let's show that matrix T is complex of size D times D. Then we can rewrite shift invariance equation using this connection between array steering matrix and signal subspace. In this case, we have the following equation: selection matrix 1. So let me call it as selection matrix and etc. without transform things. Here we know that we use only transformed matrices and vectors. So selection matrix, then signal subspace, then this unknown transform matrix T times matrix omega with tangents of special frequency. And in the right side, selection matrix 2 times signal subspace E sub s times matrix T. So here, as before, I will use green color to show that we use this equation here. So green color for E sub s times t, E sub s times t. Пока я не забыл. Ребята, а вы включили запись? Я просто не включил, те, кто онлайн. Похоже, что не включил. А? Так, давайте я пока переключусь так. Никто не включал записи? Ребята?
Я не включал.
Ага. Давайте я включу и чисто покажу там, по сути, у нас пару формул только. Это я вовремя вспомнил, то, что мы еще недалеко ушли. Так, запись у нас идет, поэтому можем пробежаться быстренько. So here, in today's lecture, we start with the connection between transformed array steering matrix and original array steering matrix, and also between the signal subspaces. So you can see that we need to multiply original one with sparse left bireal unitary matrix from the left side, and also with Hermitian operation. Then we show that the columns of A are connected with the columns of our original signal subspace, and the columns of transformed array steering matrix are connected with, let's say, transformed signal subspace. In this case, we can show the connection between these two matrices with transform matrix. Here we show what we have in the multiplication of these matrices, and this matrix T is non-singular, and it is square matrix. Then we put this equation in green box into the shift invariance equation for 1D unitary Aasp. Then let's multiply from right side with inverse of the matrix T. Inverse of matrix T, multiply both sides from right side. In this case, we will have selection matrix 1 times E sub s times T times omega times inverse of T. And from right side, selection matrix number 2, so second one, times E sub s. So if I'm not mistaken, we did something like this one also for standard Aasp. And then we say that this multiplication of T times omega times T inverse, we will call as matrix epsilon. We denote it as matrix epsilon. So this one is epsilon. And if you remember, 1D unitary Aasp algorithm is real valued algorithm. In this case, all these multiplications are real valued invariance equation. We can call it as real valued invariance equation. Then, as before, this matrix is eigenvalue preserving similarity transformation matrix. Matrix epsilon which is equal to t times omega times inverse of t is eigenvalue preserving similarity transformation. Eigenvalue preserving similarity transformation. Transformation. And one more thing here for matrix epsilon, this matrix epsilon has real valued eigenvalues. Has real valued eigenvalues, which is equal to the tangent of mu sub I over 2, where I is equal to 1, 2, up to small d. And then we have an estimated signal subspace. Estimated signal subspace which is denoted as, so let me move the page first, this one, image of QM Hermitian. No. What Hermitian times E sub S. Okay. So this thing with blue underline here. And let's write down shift invariance equation using signal subspace E sub S and this eigenvalue preserving similarity transformation. It is equal to selection matrix 1 times E sub S times matrix epsilon this is equal to selection matrix 2 times E sub S. I put this equation into the box. And also I will color it with yellow. This multiplication is real of size small d, so the number of elements in subspaces, subarrays, sorry, in subarrays, times the number of sources. And let's show in short notation that we can use least-squares algorithm to find this matrix epsilon. In this case, we'll have this last solution, and it is equal. So we have this matrix epsilon. Let's use subscript ls for least squares solution. It is equal to. So the left part is selection matrix 1 times E sub S pseudo inverse, K1 times E sub S pseudo inverse, times the right part. So selection matrix 2, K2 times E sub S. This matrix is real of size small d times small d. I put this solution into the box, and then, of course, as before, we can use total least squares or structured least squares algorithms to find these matrix epsilon. So TLS and SLS solutions are also possible. Also possible. And then we need to find the eigenvalues of this eigenvalue preserving similarity transformation. And then we need to calculate arctangent to find the special frequencies. And here we introduce a reliability test. I think this test is used for the next thing. So if we assume complex valued matrix and we calculate singular value decomposition, we always get real valued eigenvalues. So in any case, but if you calculate real valued matrix, so you calculate singular value decomposition, and in this case, sometimes you can get complex valued eigenvalues. And for this one, we introduce this reliability test. So we need to check whether our eigenvalues are real. So let's write reliability test. Reliability test with 2 underlines here. So we calculate eigenvalue decomposition of matrix epsilon, and if all the eigenvalues so if all eigenvalues here from 1 up to small g of our matrix epsilon, which is real valued of size d times d, if all these eigenvalues are real valued, then the reliability test has been passed. The reliability test has been passed. And we can find special frequencies mu sub I in the following way. So 2 times arctangent of our eigenvalue with index I, where I goes from 1 to up to small d. So why we multiply this thing with 2? Because let me find this thing here. Here we have tangent of mu sub I over 2. So first we take arctangent of our eigenvalues and then multiply it with 2. So we'll calculate arctangent of omega times 2. And otherwise, if some eigenvalues are complex, so otherwise, if we have complex conjugate pairs of eigenvalues, in this case we have complex conjugate pairs of eigenvalues in this case we need to start all calculations again. So start again, but with more measurements, with more, or we can say more reliable. Let's add here, or more reliable measurements. So here, for reliability test, I will indicate eigenvalue omega sub I with blue color, and all these eigenvalues should be real, are real values. If we have this case, then we can say that reliability test has been passed. And I will put all this part for reliability test into a box. So this thing for special frequency, but if we want to find direction of arrival, so estimation of the direction of arrivals, in this case, we need to calculate the estimation of this theta sub I, which is equal to arcsine of minus lambda over 2 pi delta and times our special frequency mu sub I, where I is 1, 2, up to d. So next, let's go to the slides 26 up to 28. Slides 26 to 28. So here you can see for the first slide, first we let's say how we calculate transformed selection matrices. So you can see for the first selection matrix, we take the real part of this multiplication with original selection matrix 2. And for transformed selection matrix 2, we take the image part of the same multiplication. And here we have an example with overall number of elements is equal to 6. And we use maximum overlap case. And we will have 5 elements in each subarray. So first we need to show a second selection matrix. It is the let's say diagonal matrix with ones for the second column, first row, then second row, third row, fourth, and fifth in the following way. And if we multiply these matrices with these sparse matrices and take for the first one real part, we'll have this type of a matrix. So you can see it is not the ones on the main diagonal. So we have something like this one. So you can see that we choose different elements in this case. And here you can see what we have for the second transformed selection matrix. Maybe let's show this thing first. 26. Slide 26. M is equal to 6 in this case. And small m is equal to 5. Maximum overlap. Then let's go to the summary of 1D unitary Aasp algorithm. So we have the same steps here as for standard Aasp algorithm. So first step, single subspace estimation, but here you can see instead of U sub s, we have E sub s, and this matrix is real valued. Then we need to find less singular vectors or eigenvectors. So in the first way, we calculate SVD for transformed X. In the second case, we calculate EVD for this T of X times T of X Hermitian. Then we solve this shift invariance equation using LS, TLS, or SLS. And the final step, we need to find special frequencies. So we need to calculate eigenvalue decomposition of this matrix epsilon. In this case, we will find eigenvalues, which is diagonal elements of matrix omega. And then we can easily calculate or easily compute special frequencies, which is equal to 2 times arctangent of these eigenvalues. And next, we have one more thing here, slide 28. I hope you see something from this from this plot. Here we have 1D direction of arrival estimation. We use overall number of elements equal to 8 here, and we have 2 uncorrelated sources. And for y-axis, we calculate root mean squared error 4 degrees. And here you can see that we change signal to noise ratio. And here we compare standard airspeed with red circle, then unitary airspeed with green, let's say, plus, then root music algorithm with purple, let's say, square. Then we have mode, which is denoted as black cross, and stochastic Kramer-Rao bound. So I think we will do a lecture with my group mate, which had this type of theme for master thesis. So he worked with Aasp algorithms, Aasp type algorithms, and also he tried to found these stochastic Kramer-Rao bounds. So this stochastic Kramer-Rao bound is something like the smallest error when we try to find direction of arrival. So maybe if we compare it with something, например, мы можем это сравнить как вот эта граница для Шеннона, когда мы считаем пропускную способность, не используя, хотя используя, да, модуляцию, мы максимально можем приблизиться к этой границе, но только в идеальных случаях можем достигнуть ее. Но в реальных случаях мы не сможем всю пропускную способность, так скажем, получить. И здесь это приблизительно то же самое. То есть мы смотрим, например, что мы можем достичь для SNR 0. То есть это максимальная ошибка у нас будет равна, так, это 0,1, 0,2, 0,3, где-то 0,35 у нас будет ошибка. И как видите, максимально приближающаяся к этой границе у нас unitary airspeed. То есть нам лучше использовать unitary airspeed, чтобы приблизиться к этой границе ошибок. А самым плохим, например, до 5 сигнала шума у нас это root music, по сути. То есть это самый плохой алгоритм, так скажем, если мы сравниваем, насколько точно определяются углы прихода. И наилучший алгоритм в данном случае unitary airspeed. И давайте запишем здесь. So let's write for slide 28. Oh, sorry. Slide 28. Here the number of array elements is equal to 8. Then the number of sources is equal to 2. We can show that they are uncorrelated. So let me check one more time. Yes, uncorrelated. Uncorrelated sources. And the direction of arrivals. So first direction of arrival is equal to 10, and the second one is equal to 15. And here we compare algorithms which use least squares solution. Least squares solutions. So we end with some summarizes for unitary aspirate 1D case, but now we need to introduce, so I need to introduce structured least squares solution. So let's write structured least squares solution. Structured least squares. Or SLS. Oh, Т2, of course. The direction of arrival. Thank you. Structured least squares solution. Before, in previous lectures, I just said to you that this type of the algorithm somehow uses the connection between subarrays or something like this one. So let me check. Just one moment. So yeah, we take to account some specific connection between overlapping subarrays. And now let's see how we can do this thing. And here we have another slides. Slides 29 up to 33. In these examples, we need to use, so we take to account the relationship between overlapping configurations. So we can say that M is equal to, so the number of elements in subarrays is equal to overall number of elements minus 1. And we use uniform linear array. Then let's start with first slide here. So, what is structured least squares algorithm? So it improves the performance of aspirate type techniques or algorithms. So here you can see that what we have, And structure is defined in terms of two selection matrices applied to a matrix spanning the estimated signal subspace. So it is it means this multiplication of selection matrix 1 with U sub S and selection matrix 2 with U sub S. So one more time. Structure is defined in terms of two selection matrices applied to a matrix spanning the estimated signal subspace. And then this SLS algorithm solves the invariance equation by preserving this structure. And for initialization, we use least squares solution. And then we can use, for example, only one iteration of SLS, so it is iterative algorithm. And using only one iteration, we can improve our estimations. But of course, we can calculate more than one iteration here. So now, let's go next. Here. In this case, you can see that we have invariance equation with selection matrix 1 times U sub S times matrix Xi, if I'm not mistaken, which is approximately equal to selection matrix 2 times U sub S. And here you can see three types of our subarrays. Here we have maximum overlapping subarray. Here, this one is not maximum overlapping, so we choose for the first subarray only odd elements, and for the second subarray only even elements. And here you can see that we have unusual configuration. And if we review our previous algorithms, so least squares solution, this thing is the easiest solution, let's say. And you can see that we want to minimize it in this solution. The error for second subspace, for totally square solution, we take to account also the errors in first subspace. So for this one and for this one, or yes, for first selection matrix and for second selection matrix. And if we look to SLS, it accounts for the specific relationship between the entries of J1 times U sub S and J2 times U sub S in case of overlapping subarray configurations. So we need to use only these, or not like overlapping. So in best case, I think we will have best improvements if we use the configuration like this one. So maximum overlapping. And then here we can assume two types of minimization. So first one, it is nonlinear minimization, and the second one is linearized minimization. So in this case, we assume this noise corrupted estimation of unknown signal source space, which is spanned by the columns of U sub S, and we introduce this error for this U sub S. And here you can see, let me check. We need to minimize this type of a matrix. So here we concatenate this matrix R, which is called as residual between the first selection matrix and the second selection matrix. And here in the second part, we concatenate it with a weight vector, which is multiplied with this, let's say, error for U sub S. Here you can see it is equal to the overall number, not the number of elements in subarrays divided by alpha times overall the number of elements, and we need to take the square root of this multiple division. And this thing, this weight factor, provides a normalization such that the minimization is independent of the two block matrix sizes. So this minimization. And for alpha, we need to take this value greater than 1. So let's maybe use, let me check. And let me check what we have here. Okay. So we calculate this residual matrix at the kth iteration, for example, and in this case we will have these values here. So you can see that we update U sub k and xi sub k, and for the next iteration we will have this big thing here, and then we use property of the Kronecker multiplication here, that vectorization of y times y2 times y3 is equal to this Kronecker product of y3 transposed with y1 times vectorization of matrix y2. So you can see that it is really complicated algorithm in comparison with previous one. So maybe let's start here. What we need to show. Maybe let's write down vectorization of and then, so yes. So now let's write our goal, and then we will go step by step what we have here. What we have for residual, what we have for vectorization things. And let me check one more time. So, okay. So here, first, this delta U sub S sub k is the subspace change at the kth iteration step. And you can see that we have this U sub k equal to U sub S plus this delta of U sub S sub k. And then let's write our goal get update of delta psi sub k and delta U sub k. In this case, we first concatenate here. And let me note that we need enough space here to write these all things. So first we start with concatenation. So keep all of this relationship between subarrays. On the top we have vectorization of our residual. Between U sub k plus 1 and psi sub k plus 1. And we concatenate this thing with vectorization of, so here k it is kappa. We call this thing as kappa. Times delta of U sub S for k plus 1 iteration. Kappa. Yes. So no. Yes. So I indicated with red color because then we also will show this thing. So it is just kappa. This one from, I think, Greek alphabet. So alpha, beta, gamma, etc. And also we have kappa. Then this vectorization thing. First, let's show what we have for the previous step. So it is really big thing here. In this matrix, we will concatenate 4 different matrices. Here we have identity matrix of size D. Kronecker product with selection matrix 1 times U I think let's write UK here for step K. And below of this matrix, we have 0 matrix. And then from the right side, we concatenate so here we have xi sub k transposed Kronecker product with selection matrix 1 minus identity matrix of size D Kronecker product with second selection matrix. And below of this thing, we have kappa times identity matrix of size M times D. So the same kappa here. It is our weight factor. This thing is multiplied with concatenation of, so here we have vectorization of delta xi sub k for the previous step, and below we have vectorization of delta u sub k. And plus all this thing plus this vectorization thing for the previous step. So the concatenation of vectorization with residual of u sub k and xi sub k and here kappa vectorization. Okay, we can do this thing. So we can move this weight vector outside of the vectorization operation. And here we will have vectorization of delta u sub k. and same kappa here. So let me check here. What I have next. So this is residuals. So let's maybe first denote what we have for residual. Or maybe we can start with vectorization. So let's start with vectorization. So if we have some matrix A with elements or with columns A1, then A2, then A3, etc. up to AN, this matrix of size M times N. If we calculate the vectorization of A, we will have first A1, then we concatenate it with A2, etc. up to AN. So one very big vector, which is complex of size Mn times 1. Then what we have for residual? These are of U and Xi is equal. So let me check. J1. J1. And maybe let's keep K and K here. J1 U sub K times Xi sub K minus selection matrix 2 times U sub K. This thing is residual. And kappa is equal to square root of small m divided by alpha times m. We call it as weight factor or weighting factor. Weighting factor. What? Yes, yes. This one is kappa, which is used here. Here, here, and here. So this weighting factor. So then we need to go back to our previous equation, and here we will let me switch here. So we denote this matrix as matrix Z. So this matrix is matrix Z, and we use this thing to calculate the value of the cost function. Я покажу чисто вот верхушки алгоритма. Мы прям глубоко лезть не будем, так буквально пару вещей. И даже как раз закончим, наверное, на этом. So new value of the cost function. After this weighting factor, new value of the cost function. With two underlines here. The cost function for step k plus 1 is equal this matrix Z times vector x minus plus, sorry, cost function for the step k. In this case, we can find vector x as follows. X is equal to the inverse of Z. Here we multiply it with C sub k plus 1 minus C sub k. Or if we have non-invertible matrix Z, we need to calculate the pseudo-inverse. And multiply with the same thing, C sub k plus 1 minus C sub k. And here we need to minimize the 2 norm of this next step of a cost function with respect to vector x. In this case, let me put this minimization into a box. In this case, if c sub k plus 1 goes to 0, we can say that z times x is equal, approximately equal, minus c sub k. So we move this one to the left, and this thing goes to 0 with our minimization. In this case, x is equal to minus matrix z pseudo inverse times c sub k. So in this case, what we have here, let's go back to our z. So we have this z, we have this cost function for the next step, or let's say yes, cost function for the next step. This is our matrix vector z, and this one is our cost function for the previous step. In this case, using this equation, what we'll have here. So let's write solution for all these things. Solution so let's maybe indicate also here. So to understand all these things, so maybe I will remove kappa from this one. This is our vector c sub k plus 1. This is our x, and this is our c sub k. So first, we use this short notation to see how we can find a solution to update our delta, this thing, delta xi sub k and delta u sub k. And all these things are equal to the following thing here. So one more time, we concatenate vectorizations. First is vectorization of delta xi sub k and vectorization of delta u sub k. This thing is equal, using this minimization, let's say minimization goal, and using this resulting equation, we have minus inverse of z times vectorization of the residual. So vectorization of the residual of the previous step values, so u sub k and xi sub k, and we concatenate it with kappa times vectorization of delta u sub s sub k. So and also we can show that this one weighting factor with red circle, and I think I did a typo in the previous equation. So here we need to write down so let me show. So here we have delta u sub s sub k plus 1, and here we need to show u sub s sub k. So previous step and next step. So here sub k, sub s sub k, and here also sub s sub k. Great. So it is just one step. So between our, if let me think, we can say that it is approximately the last step if this part is equal to approximately 0. Okay, so let's continue. For maybe we will end also here with slides. Slides 34 up to 39. So here we have the rest of the SLS solution and the summary things. Moreover, here we have comparison simulation, which show, let's say, which compare different solutions. So least square, total least square, and structured least square. So here we have this linearized minimization problem, which is equal to this z times, let's say, vector x plus this cost function for step k. It is not really cost function, but vector c is k. And here we have that the resulting least squares problem can efficiently be solved with, via a QR decomposition, which is this one. So z is equal to this thing. And in this case, matrix Z is a block upper triangle. So let's leave all these things with this slide here, and what we have next. So initialization here. Yes, here we first use least square solution and then we go inside of a structured least square solution. And then we can calculate one iteration to improve our estimates, or we can calculate more than one iteration, and maybe we can get this converge algorithm. So here the simulations, and this one, yes, really hard to see. Maybe I will try to redo these algorithms, these simulations. So what we have here? We have uniform linear array with maximum overlap, and this spacing between them is equal to lambda over 2. The number of sensors is equal to 10. In this case, the number of elements in subarrays is equal to 9. Overall, we have number of snapshots equal to 20, and the number of trial runs for this unitary Aasp algorithm with SLS solution equal to 4,000. And let me check, maybe I will just say you what we have here. So we have the same very bad performance of root music for signal to noise ratio from -6 up to -2, here up to 2, and here up to 0. So what we have here, first one is our source 1. Here we have source 2 and source 3, and they direction of arrivals are equal to 0, 10, and 20 respectively. And here I can say you that when we calculate solution using SLS algorithm with one iteration, or when we try to find converged solution, they are approximately equal to each other. So I think, no, in this case, trial runs means that not the number of iterations for SLS, it is overall number of simulations. So to get this root mean square error for, I think here what we have, it is approximately the same simulations, but here we change the number of time snapshots. So the same root mean square error for direction of arrival, but now we change it over the number of snapshots, and the best results as before for a unitary Aasp with SLS here, here, and here, and the last results, I think this one for, of course, here we fix our signal to noise ratio to 0 and reduce the number of overall simulations to 1,000. And the last one here, we assume correlated sources. So you can see here we show the correlation metrics. We fix the number, the signal to noise ratio to 0 dB, and here we increase the correlation. So from the left side, we have uncorrelated sources, and from right side, we have fully correlated sources. And in this case, yeah, we have, so yes, if we put here correlation to 0, we will have just an identity matrix for the connection between them. And if we introduce the correlation, we will have these indices. And as the summarization for SLS solution, it's really complicated thing, but from these simulations, so I will try to redo these pictures with better quality. From these results, we will see that SLS really works better than, for example, just least square solution, and it can improve our estimates just with one iteration. But of course, if you want, you can run this algorithm until it converges. And what else? So for today, I think that's over. And if you have any questions, you can ask me right now. And what else? In the next lecture, we will go to multi-dimensional extensions of these algorithms. And maybe we will just go through the signal reconstruction, maybe. But I will check it first. So that's all for today. This is really, really hard things with these SLS algorithms. And of course, from the first time, it is hard to understand how Aasp type algorithms works, but I hope we will have something like homework, a practical thing, where we will try to use Aasp algorithm for direction of variables estimation, and maybe we will try to compare it with standard Aasp, unitary Aasp, and maybe with this MVDR algorithm. And I will think what we can do more than these things for practical. It's just no idea. So